Here, if you ignore the second part, if you ignore this, we have this hypothesis, and we want to prove A.
Why is not on the cheat sheet?
Come on.
Why is not on the cheat sheet?
It's not in the cheat sheet. Come on. I need to add it then. Let's get this goal first, and then, yeah, we can just use assumption, because perhaps we already have. Okay, now we prove the first goal, and now we have to put the second goal. That's a little more.
No. Yeah, but yeah, overlap.
Then we apply H0.
Yes, because now we have B, and the hypothesis that has B at the end is H0, and what it will give me. Apply H0, and yeah, we have H. That means applying H0, now I had a B, and to prove a B, now I have to prove an A. We already have the assumptions. And done. You can use exact. No, exact with the hypothesis, the specific. Here, I am the first. In the first goal, I want to prove A, and I have already A in the hypothesis. Then you can use exact H1. Yes. Yeah, because the first goal, I want to prove A, and I already have A in the hypothesis. This is the same case as this theorem. Yeah. Yeah, here is the first goal.
Yes, yeah.
And this is the second one. The first one is easy because just use all of your assumptions.
So both of the assumptions are exact H1?
Yes.
So when you say apply, you're saying the goal will be proved if I can. Given this hypothesis, the current goal will be proved if I can prove the sub-goals.
Yes.
Yeah.
And basically apply kind of removes the implication from the hypothesis. Not removes, but says, okay, you have A implies B in the hypothesis, and you have a B. Okay. If you have a proof of A, I guarantee that the rest is proven.
So is there no version of assumptions which applies assumptions multiple times?
Assumption is by definition applying other.
If you find yourself writing assumption period and assumption period again, is there a way to do those two?
No, because that would be different goals. I mean, there is a ways to structure. There is kind of. No, but if you have multiple goals, the assumption solves the first goal, assumption solves the second goal. They're kind of different things.
So I'm curious if I have the ordering of what we're proving. So the first apply which makes the new rule defining A and B.
Yes.
Okay, and then the assumption gives you B.
No, because
What are the assumptions?
in the first goal, if you go here, now you have two goals.
Yeah.
The first goal is prove A, and the second goal is prove B. So forget about the second goal.
Yeah.
Now you have all this in the hypothesis, and you want to prove A. If you see the hypothesis, you already have A. So it's not just
Okay, so that first assumption gives you A.
no. The first assumption, yeah, but the first assumption closes the first goal.
Oh, I
You proved your first kind of sub-theorem. Hold on.
Does it make you, like, it makes you do one sub-goal at a time, right? You
Yes.
Like do both sub-goals at a time.
No.
So it'll do something once, it'll prove your first sub-goal, and then you gotta do it again to do the next sub-goal.
So doesn't some cycles so we do that application?
Yes, because when you apply, if you think even you can, even if you are in the first case that you have only one implication, your goal is a beta, I don't know, C in this case, and you have A implies C. You apply the hypothesis, and now your goal is the first part of the implication.
Which we can get again by just doing it.
Yeah, exactly.
Yeah. Very. Yeah. There's another one from the reference manual that not everything.
You want to try these ones, or we can move into?
Yeah, let's do it. Let's just bang these out.
Eh? No, you cannot get the excluded middle. Like, not A is the excluded middle is either A or not A. But this is that what they're proving is the double negation is equal to the. So. Yeah. Here.
Some small question. Is
Yes.
there a notion of proof minimality? So, because I've used a different sequence of operators to large part of the same thing, so is there a mathematical way to determine what proofs are minimal?
Not really, because this is kind of a search into a tree. I mean, probably you can do it, but I think that.
There was possible to introduce redundancy in proof. So, for example, I just blew up my proof for the next one to change the subcode if I want to. So,
Yeah.
there is no way to determine automatically the proof minimal.
No. I mean,
You could iterate over all statements shorter, but
Yeah.
it's just infeasible.
Or just mutation just to
Okay. You said rules of languages, right?
yeah.
Sequence for constructors, for example, where proofs are unique.
It wouldn't prove the original.
Is there a library? Maybe there is, right?
Maybe I'm not sure if you can guarantee that the proof is unique.
No, there's a logic called sequence for constructors.
Oh.
solution space is very small, and each proposition has only one proof. There is one.
Okay, maybe there is something.
Maybe there's like a library for it. But that's the idea, right? That somebody should write a library.
Yeah.
Right?
It might be something. Yeah.
Okay.
Yeah. Okay, with this one we can just, as usual, start with the intros. And now the problem is what we do with this not A. And what we do is let's remove the syntactic sugar of that negation with the unfold. Unfold? No. I need unfold not. 1 second. Yeah. I have here the syntax is unfold not. It doesn't like my. So basically the not was A implies false, and we have double negation is A implies false implies false. Now we have an implication in the goals. What was the tactic to remove that?
Oh, yeah, intro,
Yeah, intro again.
and then apply H0.
Yeah, but it's an easy.
Or not apply H, yeah.
Yeah. So you're saying apply H0. Yeah. Assumption. Cool. Nice.
So not A unfolds to A plus false, and then not A is flat, and unfolds again to not false. Everything else.
So unfold not, does it correspond to any of the introduction or animation?
No, unfold basically is a kind of removing the syntactic sugar. It's just a direct translation of.
Right, because the definition of false or negation is implied false.
Yeah. In the same way, the double implication, you can write it like this, but actually, if you do unfold, it will decompose into this.
How can you bind like another name to that function that you define by unfold not? Same way that you like use exact assumption.
Kind of, you mean unfold another kind of.
Can you give it a name instead of H0?
Where? Oh. Not sure. No, I think it generates automatically. I don't. It might be a way even. No intros. No, but you mean the H0?
Yeah. I would prefer to like name it F and apply F to exact.
F.
No, unfold not. I want that function that you define by unfold not.
Yeah, but unfold just doesn't even give it a name, right?
It doesn't introduce an assumption.
Just it's
Well, it was bound to my name called H0. H0
No.
functions are created.
H0 is when I introduce it to the hypothesis.
In the slide that you wrote, intro and then the operator, how do you do that? Is that command?
Here, oh, this one.
Yeah.
No, this is like
So the command is just left?
Yeah,
Oh, yeah.
yeah. These are like in your like a mnemonic or something. Yeah.
So, as a good programming practice, you probably want to name all these right? I mean, how stable this is? Like, you know, if 5 years from now I come back onto the Gandhi and I use these old defined H's, H1 is 0, put it like, then that, and they refer to them later.
Yeah.
I'm letting the programming language define the names for me and then I'm referring to them. That's kind of dangerous, right?
Yeah, I mean, yeah, but still, this kind of proofs are kind of complex. Once you prove it, probably you are not going to touch it. But yeah, I guess sometimes it's recommendable to.
It's explicitly named.
Yeah. If you don't get, so you don't get crazy. Yeah. So let's. This one, so we can try intros.
If I become a mathematician, will they teach you more of this?
Yeah.
Like they teach code if you go to mathematics school?
This is actually goes into the because this kind of oscillates on the. It's like a constructive logic. It's mathematician, but you have to kind of choose the constructive logic area. Actually, Coq has been used to prove a couple of important theorems. I think one is like a four-color theorem. I don't remember which one else. But it's kind of this is, we are just looking at the logic side, but this is more complex and right just in the middle of logic and programming.
Yeah. I'm doing the Dijkstra's. And you know, edX has a Dijkstra's course called Programming for Correctness.
Oh, yeah.
But they use LaTeX and MATLAB
Oh,
to run the proofs.
yeah. Interesting.
Say that 95% of mathematicians do not know. Meaningful.
There's a book called Software Foundations.
Yeah, I put in the links at the end. Those are very one.
So, the negation is the initial step, right? Is it, so think of negation as synthetic sugar. Which
Yeah.
is by definition, meaning that you can
Yes.
I mean, no, not elimination.
So what this does, basically unfolds the synthetic sugar and makes it into the So if you run it, see, basically two the definitions for
Actually, if you let me go to the end. This one. This is the link. Software Foundations. Let me do one more proof of this. You can do the rest if you are bored. But I want to show other things that are very interesting. So here, if the goal is a disjunction, the idea here we can use split, because basically we are saying, okay, we want to prove A and B, so we split the proof and yeah, exactly. So let's say split, and now I have to, yeah. assumption. And basically, we prove this. Those are the interesting proof. I'm going to do one thing because we're going to run out of time before seeing everything. The next step, we already did some basic proofs in propositional logic. Now we can do, in Conc we also can do higher order predicate calculus. That basically we take the same propositional logic, but we add quantifiers for all and exist. In the sense of, okay, you can prove like for all fg from natural, if the functions are the same for all the values, whatever. These are examples. And it kind of works similarly. We have intros and eliminations. And in the case of, if we want to prove that for all x, a, b is similar to implication, basically we move the for all to the hypothesis and assume that, okay, I have a proof of A.
So the comment as far as like precedence of the operation here, this can be read as x implies both A and B, or x implies A.
No, x is the A is the type of x.
Oh, okay.
Yeah,
okay.
for all x of type A, B.
Get B. Okay. All right. Cool.
And it probably is clear in the, if you see after the introduction, you see x of type A.
Yeah, well, that wasn't very cool, but it makes sense then.
Yeah, here in the example is a little more explicit about that. For all x, nat is the type of naturals in Conc. Elimination is a little more complicated because it's more related to substitution and everything. If we have a for all in the hypothesis and we have a B, we can apply the hypothesis. If there is all this part means if exists a substitution, means that if I replace in Y all the values for one A, basically it says B is a particular case of Y. This is a formal way to say it. And we can have many for alls, and even I can apply but I went for all. It works similarly, but it's a little more complex. But basically, I'm probably going to show one proof of that and skip the rest. The exist is a little, the introduction of exist is a little easy. Basically says, if I want to prove that exists one, and I can give one, it replaces the exist with a particular instance, basically a given instance. And the elimination of the exist, when I have it in the hypothesis, it creates a for all. And there is a couple of other tactics to work on this for more complex proofs, to work in the higher order predicate calculus. We can apply reflexivity, symmetry, transitivity. We can rewrite some terms. It's saying, okay, I know that this I can rewrite as this other part. We can replace things. And we have some like vernacular commands that show the current proof, or show the proof tree. I'm not going to spend too much time on these ones, but at least we can show that it's possible. So I want to prove that basically that the name of the variable doesn't matter for all x of type u. A or x imply for all y of type u, a or y. Okay, as everything we start with intros. If you see the difference, intros does automatic introduction of everything, but I can go step by step. First, I'm going to introduce the first part. Let me call it for all. Now, the goal the goal is the same. This is kind of interesting. Watch this. If I do intros, it does introduce everything. Not only introduce the first part of the application, but also introduce the first part of the for all. But that gives us in a way that it's not easy to prove. So if I go one step by step, I just going to introduce only the implication, and then because H for all, I mean, one of the hypotheses is the same, it's just without the name. The name doesn't matter, I just can apply, and because substitution, that's.
So works if you stick intros and then apply H, it'll still evaluate H.
Yeah. Let me see what can be interesting here. I'm going to leave this here because I want to go into something slightly different. Something slightly different. So let's see Coq from the point of view of a programmer. Let's talk about a little about the Corey-Howard correspondence. Have you heard about Corey-Howard? It's a really powerful idea. That's the basis of Coq and all this. That proofs and kind of there's equivalence of proof on Lambda Calculus and function application that they look the same. So if you look at your programs as proofs, we can do all the things we were doing before. And get ideas to work on these kind of things. This is a kind of brief summary of the equivalence I took from Wikipedia, but it's interesting. Basically, the most visible part is the implication. In logic, implication A implies B. It's the same thing for us, that the function that takes an A and returns a B. If I have a function, because this is constructive logic, I prove the implication. In all that picture, we have the Lambda Calculus, the titled Lambda Calculus, calculus of constructions, that's the theory behind Coq, is a titled Lambda Calculus with high order parametric functions and dependent types. Dependent types is interesting because you can make types depending on values, and then you can encode things like a arrays with a safe size. Your function takes two arrays of different size, and if the output is not the sum of the size of the array, it doesn't compile. But the whole thing, that theory gets extended, and the extended calculus of construction with inductive types, that is like infinite types, like a list that can grow, and also the other co-inductive types that are like, if I recall correctly, streams, infinite, really infinite data types. But that's the kind of the theory and how that expanded. That's here is another way that we can use proof. I mentioned quickly, but if we have B implies C, we can use exact and apply the like way of applying functions, but really we are using part of the hypothesis. All this is lower. It's a lower, works at a lower level than we were seeing before. It's kind of high-level syntaxes. As I mentioned before, you have set types and propositions, constants. You have the function application that looks like function application everywhere. Abstraction is when you define the parameter, the function type, inductive type definitions, case analysis, that is pattern matching, and recursive definitions. Code is not Turing complete. You don't have general recursion because that is not terminating, and then your proofs won't be valid. Huh? Yes, that's why we have a inductive and fixed point. Every time you declare a function, if it works on first you have to work on a inductive type if you want to do recursion, and you have to use fixed point, and you have to specify the type of recursion. Usually say structural recursion. That means the recursion is based on the construction of the data type, and that is guaranteed to terminate. There's a couple of more complicated things that I don't know the theory behind that, but you can even go further and use like a well-ordered foundation, something like that. That is a little more recursion, but it's still not general recursion. Coq is based on, it was programmed in ML and OCaml, so the syntax is kind of a little similar. This is how you define inductive types. Like your piano naturals, that you have the zero and the successor, Boolean, that's true or false, a list of numbers, that you have the nil and the const. Those are just examples. You can use, instead of like fixing the type of the list here, you can use a parameter. You have a list of A, of type A, if it's a set. That means a list of, I don't know, it can be integer, strings, whatever. And here you have kind of how do you find the generic list. Here we are using dependent types, because this is the array of elements. You have the empty array of size 0, and when you add an element of the array, you have here you have the for all. For any n, that is the size. If I take an A, an element, and an array of size n, I will get back an array of elements of size n plus 1. Here in the data type, we are encoding the size of the array.
Are this building of the library, or is
Huh?
something that the program itself?
This is an example of data type. Probably you already have a library of this,
Oh yeah, okay.
but this is kind of how you work with that. You can generate like mutually recursive types, like a tree that basically takes a forest. Probably it's easier to start with the forest. That is, either you have the empty forest or a collection of trees. You can add a tree to the forest and get another forest. And the tree is, again, you take a forest and a node, and you get back a tree. They are brutally recursive, and that can be generated in Coq. Even more, you can generate, you can write kind of predicates, propositions, in an inductive way. Like in this case, the proposition even. I mean, 0 is even 0, and then for a natural even of n means like the next of that natural is also even. And here it's called inductive because you go from the base case to you basically apply the inductive hypothesis and generate the predicate of that. Because it works, you know, piano numbers?
Pardon?
Piano numbers?
Piano?
Yeah. You have a 0 and S, the successor. Basically, S is successor of 0. It's how you define in logic naturals, because you don't have it's a way to encode the natural numbers in logic.
They'll define on previous slides, on the 2 slides. We can follow them.
Yeah, here. Basically, you have the 0 and the successor. You take a natural and apply it. I mean, basically, here is in constructors of a data type, but conceptually it's like that. So, the inductive definition has a series of implications. That means we can do pattern matching, we can do recursion on that. We can do pattern matching on the propositions. We have induction, and also the structures we can generate, extract the initial data back. This is how we define a function in Coq using kind of pattern matching. But you have given name and then the declaration of the function. Here, this function takes the predecessor from the number. Nat is the type of naturals in Coq. Here, how we would define the predecessor function. Use pattern matching. This is using also the structures, because from the type S, M, it takes out the M. We can use those constructors in our proofs, so we can either apply it. Some of them, it will be kind of equivalent to what we're already doing. And then we have it generates different tactics, things we can use to prove things. Use this construction discriminate H. If you can apply it, you can prove your hypothesis, your goal based on the hypothesis. And it has there's a tactic here that tries to simplify and apply your simplify and try to solve the goal based on what you have. And this is kind of things you get internally defined by creating the data types that way. And then the recursive, if you see here it was just a simple function. The predecessor doesn't do any kind of recursion. But if you want to do recursive functions, because we don't have a general recursion, you need to use fixed point. And this is the general syntaxis. And here's how an example of adding two numbers. If you have to specify at least one to specify where is the recursion, to tell Coq that your recursion will terminate because it's based on the structure of the data type. But yeah, this is how you define the. If you see the sum of naturals encoded in the piano numbers, this is a recursive call. Basically, you have we have other examples for even and odd.
So in that case, in that bottom one, are you using the successor to increment up or to increment down?
No, you're kind of going from the bigger to the smaller. I mean, you're not really decremented, but your recursive call goes always into a smaller structure. Kind of the first thing, you have successor of k, and now you do the call in k. You know that k is less than sk.
Could you explain again what struct means? Is it like a single call thing or something?
Struct?
Yeah.
No, this is a kind of a declaration of in which structure, in which data type, in which of these ones, the inputs, are you doing the structural recursion? Because you cannot do like general recursion. You cannot do like, okay, going to do a recursive call here. The recursive call must be in a smaller data type. The data type is always getting smaller and smaller.
Can I think of it as moving from type to 10? What's happening is like the nut is like a type, and struct then it's the body of the type. No, right? It's not,
No.
It's nothing to do.
If you see here, let me see if I have another example of trees. I have another example, but
It's basically tells it what is the fixed point one.
kind of basically which of the data types you're going to iterate on.
Yeah.
And then Coq checks that data type is like reducing. In the same way, we can use pattern matching to make the proof. I will show an example later. Induction. You will see if when we generate the data type, Coq automatically creates properties for us to use. Kind of they are destructors. Yes.
Maybe kind of after the so the pattern matching really is happening often in types here, right? This is kind of pattern matching.
Well, it's on constructors, like most of pattern matching.
Because there could be a problem with pattern matching in types because you look for parametricity.
Yeah, this actually first this is on constructors, and here.
I can view it sort of like not just dependent types and this is all crazy stuff, but so can I view it as kind of a this is not no longer on types, this is really kind of on values because of like singletons or because of some sort of a magic mapping between these.
Well, I need to look at the example. I have the example of the list of with like a generic type. I understand what you're getting. I'm trying to recall correctly the answer, but there is kind of not much distinction between types and values here.
Yeah, because it's like 4 different types.
And there is it doesn't have much type inference. So if n is a parameter, a generic parameter, it will be in the on the that, but yeah, you cannot match on a specific value internally of that. It's the same thing. You still have parametricity. You cannot say. But here, in the case of numbers, you're matching on constructors, so you don't know. You know the because you can pattern match on the outer. Basically, if you pattern match on the outer type, you maintain parametricity.
Yeah, here it's safe because it's saying it's a number, right? So you can clearly match it on constructors. Right, I think I understand. Yeah.
Let me show code, because this is based on once you define one data type, it defines like three kind of functions that you can use to prove things and program based on that. You can apply the induction principle. You can use recursive object definitions, and there's some Spanish that slip here. But it's basically the induction principle allows to define inductive type families based on what you just defined. But this is just mostly for reference. Let me remove that. That is. It's the same. Trust me. Okay, let's show some code. Here's some code about the calculus of construction, how to use kind of how calc looks at low level, and then at this point, you can, when you are proving things. You can tell calc to evaluate the terms, and you can use like call by value evaluation, lazy evaluation, or try just to compute. Here I'm defining the function composition. If you take a function from B to C and a function from A to B and an A, I can just apply all together. In Haskell, you will any functional program, any functional language can do this very easy. Here I can assign a special symbol to the composition. Just I put the letter O to make it prettier.
At level 94, is that the precedence that it takes in the evaluation?
Come in.
At level 94, is that for defining precedence in evaluation?
No, I think it's at the associative level. Basically, how strong it's associated when you have to compare, like, basically to solve like ambiguity when you have like, I don't know, multiplication and sum. You have, like, you define the precedence.
Yeah.
So the idea here was to define the identity function and prove that the function is the composition of identities is equal to the identity. One second, I haven't published it yet, but I have some of the solutions here. And there were some exercises playing around with the church encoding of naturals and proving some things. But I want to show something first that is always, I really like it. Because all this one of the advantages of this is you have your code, you have your proofs, and then you can tell calc to extract code from that, because basically actually you're kind of throwing away information. you write your program, you prove things about your program, and then you can generate. So I want to show a little how it works. This will only use the piano naturals, and let's try to prove this. Like for all natural. Either you have two N and M. You had let me see how it reads. You have either this and n is equal 0, or m is equal 0 and n is the successor m. So let's try intro. Intro again. No, intro again. No, it's intros. Now is let me just I'll just copy the solution. I'm going to cheat. We introduce n. We do the case analysis of on n. So n can be 0 or the successor of n0. So now we are here in the first proof when n is equal 0, because case, if you see these are the pair of numbers we define in 0 and successor. It decomposes in cases. It basically tries to it's the programming equivalence of doing pattern match and use 0 and one thing and the successor the other thing. Here it's very simple because you want to prove saying we have a 0. We got to take out this existential and they say exists as 0 and tell Cogdat to reduce that. With omega, we evaluate the goal and reduce that. Those are the kind of tactics to work with this. But now the second goal, we introduce n0, get the for all, and it's the same case. We introduce the existence 0 and we tell Cog to reduce. That's a proof of this. But once we are there, we can define the. One second, let me double check. Okay. Let me show that I don't have anything. So I extract the code and here now we have that predecessor. Oh, is it too small? Yeah. I can open here and something. But basically, it's just throwing my home directory. The code generated from that. So this is Haskell. You can extract on Scheme, OCaml, and Haskell, and there's plugins for F#. I think for Scala too. Which one? Oh, this is the explanation. Here is the comment. Singleton inductive. It's like a no, I think it's part of the template. This is needed because It's a witness for, I don't remember.
It's not needed.
Yeah, but it's part. I think it's part of the template. And probably you can use it later. But yeah, based on the proof, you generate this code. It's kind of the interesting thing. Well, I mean, based on all this and our definition of predecessor, it can extract based on what we wrote. We know that it's correct because we proved that's correct, and the translation of that into code is this. I like it. It's nice. The code itself, the problem it has is like because all types are inductive, the performance is not the best, but this is one of the very powerful things that they use this to generate correct code and that is proven correct. There is project with this. Usually, right now, they don't generate all the code in Coq. Basically, you have one specification. They model that specification in Coq. They prove that's correct, and then the implementation itself is done like a regularly. Yes. Yeah, it's a little tricky because it uses omega, that is kind of a reduction of expression, and uses case to decompose the. Yeah.
I'm kind of having trouble wrapping my head around all three of those.
Yeah, because I kind of did a quick pass for the rest, but case decompose n in case 0 or successor. You do a pattern match. You have two goals: the case of prove the case of 0 and prove the case of successor. And basically, what you have there is an existential. It says exist an m natural. So to remove the existential, you give a proof. In this case, exists 0, and you replace the existential with 0. And now you have an expression: 0 equals 0, or 0 equals 0, and well, actually 0 equals 0 and 0 equals 0, or 0 equals 1. And then omega reduces all that into one expression that basically is 0 equals 0 is true. The other one is pretty similar. Once you get intro and remove the for all, again, you exist in 0. And then with omega you reduce till you find the equality. If you see the expression here has three things, and this is the one with equality, and omega reduces and finds the correct one.
How hard would it be without using omega?
But I don't think it would be hard. It's just more cumbersome because you have to start splitting and proving. I think because. Actually, let's do it without omega. Last case, we can do. I think we can do right, right? Let me try right. Yeah, and then that is Tautu. I don't remember exactly. Yeah, because basically now you are trying to prove that A is equal to A, and it's like a tautology. It's not that. It wasn't really that hard, but omega does the selection for you automatically.
So what is that function doing?
This one.
Yeah.
This one is basically says. For naturals existe a natural that either both are 0 or 1 is the successor of the other. Basically says that for every natural you have a predecessor if it is or 0. Yeah. And
So, object calls send me for the solution?
Yeah, of course. And
I tried playing through cock.d file, and I think there are some errors in it that's causing it. Like the definition of composition won't work.
Okay.
D and C aren't defined.
You used to add B and C to the set.
Yeah, so I did that, and then when I went to go through theorem 4, since ID
it's not defined.
just point back to the same thing. It doesn't. Then the ID function doesn't match what's expected up in the composition definition because it's expecting two distinct sets. I didn't get that.
Cool. Well, in the slides at the end, I put some references of the documentation. It's very complete. This is a very good tutorial, very small. There is the main tutorial is very complete. Here you have an online version. It's like in kind of JavaScript web version of Coq. And this is the course that we mentioned, Software Foundations from Benjamin Pierce. That is very interesting and use Coq to prove the foundations of computer programming. Well, thanks a lot. Hope you had fun. And yeah, thank you.